applied cryptography and this sort of thing. So today I want to kind of just talk about the low-level key management stuff that we do kind of underneath everything, just to give a little bit of idea of like when we're trying to make decisions, how do we make those decisions, what should we think about? So to start, let's kind of think about the depressing state of things right now. Look, in Web3, basically everything that you do is mediated by a key, right? You want to generate a transaction, you want to, anything you want to do, somehow you generate a signature for it, so you have a key, okay? Unfortunately, key management is hard, or at least it can be, and this means Web3 is hard. Okay, this seems a little silly, but I think this is the experience that many people hit, and so this is kind of where we start from. Okay, so how do we make it easier? Well, maybe one way to start thinking about like teasing these things apart is thinking about what it would look like to have really great key management. What would we want? Well, we want it to be easy to implement, we want it to work with any chain, we want access control and automation, and we want backups, and we want audits, and we want security. And we want probably other things too, but let's come back to security. So what does it mean for it to be secure? Well, to answer that question, we have to say, what is the attacker able to do? We need an attacker model. So an attacker model says, this is what the attacker can do, this is what the attacker wants to do. So for example, in TLS, we say the attacker controls the order of packets sent over the network, and still we should be secure. And many cryptographic protocols, if we're using a cryptographic primitive, we say the attacker can't break that primitive, otherwise we probably wouldn't use it. In economic security protocols, we have this idea that the attacker just wants to maximize its profit. The attacker is rational or something like this. Okay, so these are the sorts of things that we say about an attacker, and these let us think about the security of concrete protocols. So let's start with a really terrible one that I hope nobody does, and that is just give everyone a copy of all the keys, and then everyone just gets to make transactions with those keys. And this really happens a surprising amount. And the reason, I guess, or one of the reasons, is it's super easy to do, right? And like it works anywhere, and it's compatible with automation, and it probably gives you disaster recovery because like not everyone's laptop is going to crash at the same time. But of course, it gives you other terrible things, like you can't have access control, right? Once I give you a key, I cannot be convinced that you've deleted it. And of course, I can't audit anything because if everyone has a copy of a key, then anything that happens could have been done by anyone. But okay, so how about security as such? Well, is this secure? Not quite the right question. Instead, we want to say, under what attacker model would it be secure? Like, what do we have to believe in order to think that this could be secure? Well, we have to assume at least that everyone who gets a copy of the key will remain honest forever, right? Because they're going to have the key, and so if they become corrupted, they steal the money. Okay. We also have to think that an attacker won't be able to just take control of their machines and steal the key, right? If they can, then we're kind of sunk. Okay. So this is, well, intuitively, like we don't actually believe these things, and this is why we say, okay, this is crazy, this is not secure. If anyone here is doing that, don't leave now, or that'll like reveal to us that you're doing it, but like sneak out later and fix it. Okay, good. So what do we do instead? Okay, so one thing, maybe the next logical step would be, we said, well, if the attacker could steal the key, life would be bad. So maybe let's make it such that each of us has a piece of the key. And then the attacker has to steal many pieces in order to put the key back together. And this is called secret sharing. So concretely, in this very simple model, we're going to say we're going to first like put all the pieces of the key back together, and then we're going to use the standard signing procedure to generate a signature, and then we're going to make sure to delete that reassembled key so that the attacker can't steal it. Okay. And so an example of secret sharing, just like in terms of how do we implement this, is like the simplest example is additive secret sharing. We just break the key into two pieces, and you sum the two pieces, and there's your key. This has a big downside, that if I lose one of the pieces, I've lost the whole key. So it kind of increases the likelihood that I lose my key compared to just keeping a single key, because now there's two things to lose, right? So an alternative that is kind of nice is we break the key into many pieces, and then some subset of sufficient size is sufficient to sign. And this is called threshold secret sharing. So the classic approach here is Shamir's secret sharing, and in one picture, this is Shamir's secret sharing. I'm not going to go into it, but basically polynomial, random, the evaluation at 0 is the secret. I can just give out other evaluations. If the polynomial has degree k-1, then k shares is enough to reconstruct the polynomial and get the secret. So there it is, Shamir's secret sharing. And this is really nice because now we actually get this threshold property that we want. Okay, so again, when is this secure? What do we have to believe about the attacker? Well, we have to believe that the attacker can't steal enough shares to reconstruct the key. And we also have to believe that the attacker can't just steal the reconstructed key at the moment that we're signing it. Because remember we said we're doing this naive thing where we're just putting the key back together. Okay? And so the first of these assumptions, we can actually relax a little bit just by using a fancier protocol that lets us re-randomize the shares every once in a while. But the second one is kind of fundamental because we're reconstructing the key. So there's this tiny sliver of time where all the attacker has to do is steal one key. So how do we get around that? well, we use something a little more complicated. We can use something called a threshold signature scheme. So the idea here is we're going to break the key into shares, just as before, but now we're going to use multi-party computation to actually generate the signature without ever reconstructing the key, okay? So what is multi-party computation? Okay? As many of you know, this is a cryptographic protocol, or one of a family of cryptographic protocols. We have a set of players. Each player has a secret in their head, and everyone agrees ahead of time on some computation queue, which in this case is going to be the signing procedure. So the players sort of all run the protocol, and at the end, everyone comes out with the same answer, which is Q applied to all the secrets, so in this case, the signature. But importantly, the key itself was never materialized during this protocol. The cryptography lets us evaluate the function without sharing the secrets among, or without, revealing any of the secrets. Okay, good. So again, when is this secure? Well, we have to believe that the attacker can't steal the shares, just like before, but now the key is never explicitly reconstructed, so we don't have to worry about that little sliver of time. But we do, unfortunately, have to worry about something else that I've been sweeping under the rug the whole time, and that is, roughly speaking, complexity. So these are potentially very complex protocols, especially in the case of something like ECDSA, which was never designed to be a good signature scheme. It's just a shame. And so like we actually have to worry about kind of two variants of this issue. One is that the protocol itself could be theoretically insecure, like it's just not correct cryptography. We could also worry that the protocol is not correctly implemented in spite of being correct cryptography. And both of these things have actually happened in the wild. But since we're at a conference that includes verification, a natural question is, can we verify these properties? And the answer is sort of, but not quite right now. So like verifying the theoretical security of a complex cryptographic protocol is still in the realm of research question, and verifying the implementation of some complex distributed system that involves cryptography and all sorts of things is, again, something where, depending on what you're trying to verify, it's actually quite hard to like actually write a mechanical proof for these things. It's becoming more possible over time, and so this is the sort of thing that we should be pushing towards, but today, yeah, the implementations don't really give you the kind of strong guarantees that you might want. Nevertheless, this is a really nice direction that we hope to go. Okay, so we started getting into this like kind of mire of complexity by saying, well, look, the attacker could steal keys, and okay, so what if we can just say, look, we're going to prevent the attacker from stealing the keys? That seems a little bit simple, but this is the idea behind a hardware security module, or secure hardware generally. It's a piece of hardware that stores the key, and now the key is a physical object. So if the attacker wants the key, they have to steal from a physical object from me, which seems like kind of a nice model. And these things are all over the place. Your credit cards have them, your cell phones, both in the SIM card and in the phone, ledgers and HSMs and trusted platform modules. All of these things are one variant of secure hardware or another, and they all basically give some interface that's like, you can ask for a signature, but you can't ask for the key itself. So once the key goes in, it doesn't come out again. Okay, so what do we have to believe for this to be secure? Well, we kind of have to believe that the attacker can't access or steal a physical object, and here there's a small sidebar. There are a lot of attacks against secure hardware elements. Almost all of those involve stealing the thing, bringing it to a lab with an electron microscope, and doing some ugly stuff to it. So here I'm like explicitly assuming the thing's not going to get stolen. And the way that you can back up that assumption is like, well, for example, you can use Amazon, who has HSMs in their data centers, and they have men with guns outside the data centers, and nobody's going to steal the HSMs because it's really tough to get in there. The other thing that you have to believe is that the HSM software does not just allow the key to escape. And again, we can ask, is this something we can verify? And the answer, it turns out, is yes, for the most part. So this is something like an information flow control type property. What that means is we make a formal statement like, the secret in the software will never flow to the network or something like this. And this is actually the kind of thing that the academic community has spent a lot of time in the last decade and change, maybe 2 decades, working on. And we're actually pretty good at it at this point. Well, not me, but other folks. One other thing that I should definitely mention is something with an HSM, if I have a physical device, now I worry that a meteor hits the physical device and the physical device is gone. And there are different answers to this question depending on what the HSM might be. But one is, if you go to a cloud provider, somebody like Amazon, KMS has multi-region HSM. So they do geographical replication of the keys. And if something happens on the Eastern Seaboard and US East 1 isn't available, I can go to Ireland and US West 1 and I can get the same key from them, at least if I thought I had to set it up that way. Okay, so to recap, this was sort of a whirlwind, but is it secure? Not quite the right question. Instead, is my attacker able to do something, right? And so what this means is the first step is to understand what the attacker can and can't do. And finally, this has been implicit up to this point, but explicitly, complexity counts as an attacker. Choose the simplest solution that you can, because every extra line of code is an extra opportunity for bugs. Every extra bell and whistle that you don't need is something that could turn around and bite you. So with that, thank you very much.